Welcome everyone to the morning, afternoon, evening, midnight session, wherever you are in the world, of the ICTS meeting on trapped atoms, molecules, and ions. It is my privilege to introduce Professor Stefan Willitsch. He is at the University of Basel in Switzerland, and the I mean, so Stefan, I know from a very long time, and there are some very unique things about the kind of physics which Stefan does. But before I get to that, let me just tell you that he did his PhD from ETH Zurich with Friedrich Merck, and followed by a postdoc with Tim Softly at Oxford. And then he was a lecturer at University College London, followed by his position at University of Basel, where he continues to this day. So Stefan, what is unique about Stefan is that he has taken the business of ion trap to a domain where few even today will want to go, which is in the regime of reactions. And he is a chemist, and and he brings the solid. He really is a little bit stands apart from a lot of people who come in with atomic physics and then do ion trapping. He is more than ready and happy to explore with molecules and do reactions which most people will not really dream about. He works with trapped ion crystals, and that is his crucible, I would say, and builds up experiments around that, both beam and hybrid trap experiments. And with that, I think I will hand it to Stefan.
Thank you very much, Sadiq, for this very kind introduction. It's a pleasure and a delight to be here with you today, at least virtually, and participate in this school. I'd like to give a big thanks to the organizers for this opportunity. And I'm very excited about this program that you have put together. I think this is, in spite of all the mayhem that we are experiencing all around us at the moment, this is a really fantastic thing to organize. So thank you very much. So I was asked to talk about molecules and ions and ion atoms, and I will do exactly that, right? I take the best synthesis of all of these words and talk about cold molecular ions and traps, methods, and applications. And so before I start, let me maybe say a few words about where I come from. So our institute is based in Basel in Switzerland. Basel is a nice medieval town at the fringes of Switzerland, I should say, right at the border between France and Germany. Yeah, as I've said, it's a medieval town core. It's right at the River Rhine. What you see here in my background is the historic building of the university right at the riverfront. So if you ever come to Switzerland, is a place well worth visiting. And yeah, if you have time, then stop by our institute as well. Okay, so what I will be talking about today is cold molecular ions and traps, and their applications in both physics and chemistry. As Sadiq has already hinted, I'm a chemist by training, but not only, I'm also a physicist by training. So I've had this ambivalency all my life. And I will, also in my talk, explore this interface area between physics and chemistry and see what one can do with cold molecular ions in both of these areas. So why are cold molecular ions and traps interesting at all? And this is a field that has started to emerge some 20 years ago and has been growing ever since. And there are a couple of, I would say, very exciting applications that one can do with this technology, and that all build on the unique properties of these cold molecular ions and traps. And I mean, one big advantage of this technique is that one can address single particles in the trap and exert a control on the quantum level over them. And that allows one to do quantum logic experiments and develop quantum technologies for these trapped molecular ions. And that is particularly interesting in the framework of precision spectroscopic measurements. But then they also offer opportunities to study interactions between ions and neutrals, both molecules and atoms, in a new physical regime at very low temperatures. So one can study collisions and even chemical reactions. And what the past years have shown is that one can study some rather exotic chemical processes in this regime, that the quantum character of collisions becomes important. And one important aspect that I will also be dwelling in my lectures on is that this environment and these methods offer quite nice ways to probe fine details of intermolecular interactions that otherwise would remain obscured. And then finally, they also offer opportunities to study and indeed control chemical processes also of very large or of larger molecules, right, in ways that have not been possible before. And that means one can control the quantum state of the molecules, one can control the collision energies, and therefore one can also establish ways to control the outcome of collisions and chemical reactions. Okay, so in my lectures, I will mostly dwell on the first two topics here. And my lecture is split into two parts, one today, the other one on Thursday. Today, I will talk about basic techniques, experimental techniques relating to cold molecular ions and their applications in spectroscopy. And on Thursday, I will talk about cold ion neutral interactions. And so the program for today is I will talk about the cooling and the trapping of molecular ions. You've already heard a lecture on ion trapping by Didi Leibfried yesterday, which is an excellent preparation for many of the things that I will also be talking about today. I will then really focus on molecules, molecular ions in the traps. I will talk about the internal state preparation, spectroscopy, precision measurements of cold molecular ions, and then I will finish with some new experiments on ion quantum technologies and quantum logic spectroscopy. Okay, so there's a lot of literature in this field already. I've put together a collection of books, which you might want to have a look at if you want to delve more deeply into the subject. And there are many reviews and primary research articles that I will be referring to over the course of my lecture. And you can download the slides from the website of this meeting so that you also have them for yourself later on. Okay, so let's start and begin with a few words on the cooling and the trapping of molecular ions. And I think the salient basics about ion trapping and cooling of ions in traps have already been explained by Didi Leibfried in his lecture yesterday. So I will not dwell too much about that, and I will primarily focus on molecular aspects, as I've said. So, but just to briefly recapitulate. So the salient technique that we use in essentially all of our experiments are Coulomb crystals of ions in traps. And what you see here are some false color fluorescence images of Coulomb crystals of laser-cooled calcium ions in the traps. This is a single ion, it's a string of 6 ions, it's a larger three-dimensional crystal of a few hundred ions. And so what these are is that they are essentially ordered structures of cold ions in trap, right, which form at very low temperatures under a tight confinement in an ion trap. And what all these Coulomb crystals have in common is a couple of neat features, right? They can be very cold, right? Typically millikelvin, but if you work hard, then down to microkelvins. You can keep them in a trap for very long periods of time, right? Easily hours. And as you can see on these images, right, what you can do is you can really observe single particles, right, and therefore also address and manipulate single particles on the quantum level. And that is very neat features that we capitalize on in all of our experiments. Okay, so just a very few basic words about how these ion traps work. I trust that Didi has already covered this yesterday as well. So we want to trap the ions. And since ions are charged particles, the obvious way to do this is to choose some sort of electric field to do that. Now, there is a catch, right? In electrodynamics, you have the Laplace equation, which essentially states that the Laplace operator acting on the electric potential in charge-free space has to be 0. So that means that essentially that with just static electric fields alone, you will not be able to form a minimum of this potential in 3-dimensional space in which you could confine the ions. So what can you do? So the one solution to this dilemma was the development of radio frequency ion traps, right? Starting with the seminal work of Wolfgang Paul in the 1950s, which were subsequently also awarded the Nobel Prize in the late 80s. So his key idea was to use radio frequency fields to trap the ions. So and in most radio frequency ion traps used today, they are typically linear Paul traps, as they are called today. So they are typically an arrangement of 4 electrodes, cylindrical electrodes, which are arranged in a quadrupolar configuration. And then radio frequency voltages are applied to adjacent rods, always with a phase shift of 180 degrees between adjacent rods. And they create an inhomogeneous time-varying electric field in the center of these electrodes. And they are arranged in a quadrupolar configuration to give a quadrupolar field. And what happens then to the ions is shown in this movie schematically. What you see here is the potential in the XY plane. So the XY plane is the one perpendicular to the trap axis. And if you switch these fields fast enough, that what it creates is a saddle point, a rotating saddle point that dynamically, and the switching dynamically confines the ions in the center. And you see here this little ball, this represents an ion, and the potential switch fast enough so that this ion cannot get up. It's confined dynamically. So that's the principle of a radio frequency ion trap. And so in the XY plane, so perpendicular to the trap axis, one uses these radio frequency fields to confine the ions. Along the axis, one can apply static potentials, which are applied to different segments of these electrodes to confine them also along the longitudinal axis of the trap. So that's the principle of this radio frequency ion traps, and that is also a working horse technology in our experiment. So one can then solve the equations of motion of such an ion in such a radio frequency trap and then work out the trajectories. There are analytical solutions for that, and such a trajectory is approximately given by an expression like this. So the important thing is that the motion of an ion in such a radio frequency traps in principle is separated into 2 components. One of them is a slow oscillation, a thermal oscillation, if you like, a thermal motion, if you like, of the ion in this trap, which is termed the secular motion. But superimposed on that, we have a fast oscillating component, and that is the so-called micromotion. And this is a motion, this is the motion that is driven by the RF field. So it occurs at the frequency of the RF fields. And this is a unique feature of ions in RF traps, to which we will come back many times over the course of this lecture. Can be a blessing and a curse. Yeah, it's a blessing because it makes this trap works to start with, right? But it's a curse because it's also something you have to deal with in experiments. Okay. From the solutions of the equations of motion of this ion in the trap, the so-called Mathieu equations, you can then define so-called Mathieu parameters A and Q, which are defined as given here. You can see these parameters depend on a bunch of experimental parameters like the voltages that are applied to the trap, the radio frequencies, the mass of the ion, charge of the ions, geometric parameters of the trap. And the significance of these parameters is that only a certain combination of these experimental settings lead to a stable trapping of the ions. And these regions of stable trappings in terms of these A and Q Mathieu parameters are usually cast into stability diagrams like shown here. And when you operate your ion trap, you always have to be sure to operate it with A and Q parameters that lie within one of the stability regions of the trap. Okay, so this is just to say that you can't trap ions all the time, right? But only under specific conditions when the stability criteria are met. Okay, so in order to understand how these radio frequency ion traps work a bit better, what one can do is one can then perform a time average over this micromotion. And then this leads to an effective time-independent pseudopotential. And since one likes to construct these traps in a way that in the end what one gets is in harmonic confinement, is that under these conditions one then gets a pseudopotential which is essentially harmonic in all directions, right? So by construction of these traps. And so essentially we have an harmonic confinement of the ions in this trap, and this is always nice because harmonic motion is something that a physicist can well understand. Good, and also this is something that we will need later on more often. So cooling ions in the trap. So Didi Leibschmidt has yesterday extensively talked about laser cooling of ions in the trap, so I will not reiterate that. Just a few important points for what will come in over the course of this lecture. So all experiments start with laser cooling a suitable atomic ion. And the typical ions that are used in these experiments are alkaline earth ions, because they have a simple energy level structure corresponding to an alkali atom, in which it is usually rather straightforward to implement a closed optical cycle, which is necessary to achieve Doppler laser cooling. And our PET ion is the 40 calcium ion. You see its energy level structure here. So you can implement a Doppler cooling cycle by exciting from the ground state, the 4s doublet as 1/2 state, to the excited 4p doublet p 1/2 state. So you have a laser around 400 nanometers, which you use to drive these transitions, scatter photons on this transition, and in this way achieve laser cooling. Then we also have the 3D levels, and from the 4p level, an ion can fluoresce down here, spontaneously emit the photon, populate this level with a certain probability. So here, the population would be trapped because going from here back to the ground state is not allowed, at least not in the electric dipole approximation. So one needs another repumper laser to pump the population back in order to close this laser cooling cycle. So this is how typically ion laser cooling works. In this case, in the example of 40 calcium ions, this is also what we use all the time. So maybe another note is that when you laser cool neutral atoms, right, say in a magneto optical trap or so, then you usually have an optical molasses configuration, so 6 counter-propagating laser beams to cool along all 3 directions, and to cool along all spatial directions. If you cool large ion clouds in such a trap, this is usually not necessary because the Coulomb interaction between the ions couples all degrees of freedom. So in these cases, it is often sufficient to just have a single laser beam along one axis of the trap. So this simplifies the experiments a bit. Okay, so that works well for atoms, atomic ions. However, if you would like to laser cool molecular ions, then you have a problem. That molecules are complex beasts with a complex energy level structure, and there are only few molecules in which closed optical cycles can be implemented. And as of today, this hasn't happened in a single molecular ion, at least to the best of my knowledge. So laser cooling, direct laser cooling of molecular ions is therefore not really the way to go forward. But thankfully, there is an alternative technique, and that is sympathetic cooling. And this is highly successful and has become a real working horse in this field and also broadly applicable. And I should point out this specific paper, right, which is now a landmark in the field. I think it's fair to say it's now some 20 years old. And this was the first time when a Coulomb crystal of molecular ions has been produced by sympathetic cooling. And this is now what essentially everyone uses in the field. So how does this work? The idea is very simple. So you have an ion trap, you have laser-cooled atomic ions in this ion trap, and then you load molecular ions in the trap. And you keep laser cooling the atomic ions, And by collisions between the molecular ions and the laser-cooled atomic ions, kinetic energy is all the time exchanged between them. The coupling between the ions is very strong. It's a Coulomb interaction, so energy is exchanged very efficiently. And this kinetic energy is then, in the end, transported away by laser cooling on the atomic ions. So what one gets in the end is what is called a molecular or a bicomponent Coulomb crystal. And what you see here is such a false color fluorescence image of a Coulomb crystal of laser-cooled calcium ions, and this is the fluorescence that you see. And in the center of this crystal, intercalated, you have molecular ions, in this case nitrogen ions, which do not fluoresce because they are not laser cooled, but you can see them in the regions where they displace the calcium ions and are sympathetically cooled and intercalated into the crystal. So what one can do now is one can make simulations of these crystals, and simulations shown here. And in the simulations, one can make these molecular ions also visible. And by a rigorous comparison between experiment and simulations, one can exactly work out how many ions there are and how cold they are. So let me say a few more words about how these simulations work. This has also become quite a widespread tool in the field. Essentially, what one does here is a type of molecular dynamic simulation. So one solves the equations of motion of the ion ensemble in the trap under the action of laser cooling and some heating mechanisms. So and the typical force model, which sets up the equations of motion, is shown here. So one has typically a harmonic potential for the trap. This can be the pseudo potential or time-dependent potentials. Then one needs to take into account the Coulomb interaction between all the ions. And then one needs to model the laser cooling and heating mechanisms. And there are different ways how to do this. Different people have found different approaches to that. The easiest thing is just to have a friction force for the laser cooling and then some stochastic force that effectively takes into account heating mechanisms in the experiment, right? Like electrical noise and what have you. And from such a simulation, and I show you here a movie of such a simulation, this is a cloud of calcium ions, which is under the action of laser cooling in such a trap. And then one gets the trajectories of the ions, and which you can then turn into this movie. And based on these trajectories, you can also then go forward and simulate your Coulomb crystals, right? So and this shows simulations of this crystal here. This is an experimental image, and these are simulated images under different secular temperatures of the ions in the trap, and then one can see that the crispness and the sharpness of this image strongly depends on the temperature, and by comparing those, you can then figure out that this crystal probably has something like 7 millikelvin secular temperature. And the same also, so already hinted before, right? I mean, you can then simulate, for instance, bicomponent crystals with different number of sympathetically cooled ions. And again, by a careful comparison between the experimental image and the simulated images, by really looking at fine details between the simulations and the experiment, you can then work out that this particular crystal has around 24, maybe plus minus 1 nitrogen ions in the center. And the simulations, they work astonishingly well, and one can really get very good insights into the properties of the Coulomb crystals in that way. Okay, so that is maybe a good point to ask questions if there are any.
So, so far, I think, okay, there is a question. Okay, so let me ask you, do ions radiate electromagnetic waves when it is in the trap?
Sorry, say again?
Does an ion radiate electromagnetic waves when it is in the trap?
Yeah, I mean, a laser-cooled ion, for instance, always emits, if you laser cool it, always emits radiation, right, in that way. But is that what this is about?
I think it's basically about an accelerating ion. It's not very clear from the question, but because...
Yeah, I would think so, yeah.
Yeah, but it's so small that it won't matter in these situations.
Yes, exactly. Yeah, yeah. It's a minute effect. Yeah.
Yeah, I think we can go on, Stefan. There are no further questions
Okay.
now in the chat.
Very good. Thank you. Okay, good. So now we have sympathetically cooled the translational motion of the ions in this trap. Now, yeah, let's talk about a bit about how we control the internal motion of the ions. Because one feature of this sympathetic cooling is that it only affects the translational motion. And so far, I am not aware of any experiment where one has managed to sympathetically cool the internal motion of molecular ions in that way. And the reason is that the Coulomb interaction, which mediates these collisions and the cooling in the end, is isotropic and acts at long range and only very, very weakly couples to the internal motion of the ions. And with internal motion, I mean predominantly the rotational motion and the vibrational motion of these molecules. Okay, so what can one do, right? Because I mean, it's not very helpful if you have a translationally cold ensemble of molecules which are internally hot and where the population is just distributed over many different quantum states. And that has been a major problem in the field for, I would say, 10 years in the noughties. And by the end of the noughties, around 2010, people have started to solve it by various means. And one of the first methods was rotational laser cooling, which has been pioneered by the group of Michael Drefsen and also by Stefan Schiller at about the same time. And the idea is that, okay, you start sympathetically cooling your molecular ions to start with, and then you use optical pumping, right, on the Coulomb crystallized molecular ions in order to pump the population in only a few quantum states. And this is an experiment that has been done in Michael Drefsen's group about 10 years ago on sympathetically cooled magnesium hydride plus ions. What they did is, as I've said, they sympathetically cooled the magnesium hydride plus ions in the usual way. And then they introduced an infrared laser. And this infrared laser was pumping on a specific rho vibrational transition of the ion. So we have MgH plus is a diatomic molecule, so it can vibrate, right? And you see here the vibrational quantum states, vibrational ground state, first excited vibrational state. And then, of course, it can also rotate. And so you have different rotational states, both in the vibrational ground state and the vibrationally excited state. And they were now introducing a laser for rotational cooling, which was addressing a specific rotational vibrational transition, namely from the J-2 level in the ground state. So this is the second excited rotational state. And this was then pumping the molecules to the first excited vibrational state and there in the first excited rotational state. So one quantum of rotation would be taken out of the molecule by this excitation. And from this excited state, the molecule can then emit photons again spontaneously. And by spectroscopic selection rules, it could either only fluoresce back to the J-2 level from where it started, or to the J-0 level. Okay? And the aim of this experiment was in the end to put as many molecules into the J-0 level. So if the molecule fluoresces back to the J-0 level, it's fine. Then this is already where we want it to be. If it goes back to the J-2 level, then it can be pumped back. Yeah. So from that perspective, we can pump all the population in J-0. But then in thermal equilibrium, from which we start, we have a distribution of populations. And we not only have population in J-0 and J-2, but also in many other rotational states. So what do we do about them? There's also black body radiation in the experiment. It's a room temperature experiment, and black body radiation can couple the different rotational levels and can pump populations in between those levels. So J-0 would get depleted after time by this pumping, but black body radiation would then pump population from neighboring levels, say J-3 and J-1, into J-2, from where it would eventually be pumped into J-0. Yeah? And so after doing this for a couple of times, right, on the order of a minute or so, the population would then accumulate in J-0 by this combined optical pumping of this additional laser and the black body radiation. And in this particular experiment, they managed to increase the population in J0 from maybe 4% to about approximately 40%. Yeah, so a factor of 10 increase, which is already a big improvement compared to what we had before in thermal equilibrium. So this rotational laser cooling. You can further improve this scheme by introducing additional cooling lasers. And for instance, in Stefan Schiller's group, they have managed to prepare, in their case, HD plus ions with a state purity in J0 on the order of almost 90% or around 90%. Okay, good. So another approach has been developed in our group around the same time, and it followed a completely different philosophy. So our approach was to avoid this whole problem from the very beginning. Yeah, we did not want to start with an internally hot ensemble of ions. So what we tried to do is we tried to produce the molecular ions already to start with in a specific quantum state, and then keep this quantum state as long as possible. So, and in order to avoid having to do any optical pumping on the internal degrees of freedom. So how can one do this? The method that we adopted is called threshold photoionization. And the idea is the following, that you photoionize the molecules, the neutral molecules, to generate a molecular ion inside the ion trap ultimately. And you do this photoionization in a way so that by virtue of selection rules and energetic constraints, which are also always present in the photoionization process, you produce the molecular ions only in a specific quantum state. Okay, so let me become a bit more concrete. So one of our favorite molecules is nitrogen, as you have already noticed, and the nitrogen molecular ion. And one of the big advantages of nitrogen is that it's an apolar molecule. It does not have a dipole moment, and therefore it does not couple to black body radiation. Yeah. Remember, in the previous rotational laser cooling scheme, black body radiation was essential, right, to redistribute population. Here, we want to avoid this, and this is why we choose a molecule which doesn't couple to the black body radiation field, because it's not polar. It doesn't have a dipole moment. Okay, so, and one can then devise a photoionization scheme in nitrogen. So never mind all this spectroscopic notation here. Suffice to say, we take a laser beam from which 2 photons excite neutral nitrogen to an electronically excited state. And in this electronically excited state, we pick a specific rotational level, and then we take a second laser beam to ionize the molecule with 1 photon to populate specific levels in the ground state. And what you can see here is what is called a rotational resolved photoelectron spectrum. Okay, so there's a spectrum that you get out of this photoionization process. And what you see here are different spectra taken out of different rotational states here in this intermediate electronic state. And every line that you see in this spectrum corresponds to the formation of the ion in a specific rotational state. Yeah, for instance, in this one, if you go via the second excited rotational state here in this intermediate state, and if you then ionize the molecule, then because of photoionization selection rules, you can produce the molecular ion either in the rotational ground state, second excited rotational state, or the fourth excited rotational state. Now suppose you do just that, you ionize via this specific intermediate level, and then you choose the ionization frequency, or the frequency of the ionization laser below this first band here, right? So this is essentially, this is the ionization threshold of the molecule. And if your ionization energy is below the if your laser energy is below the ionization energy of the molecule, of course, you are not producing any molecular ions, right? And so essentially nothing happens. Yeah, we only, in the experiment, we only then have a Coulomb crystal of laser cooled calcium ions, no molecular ions. And if we then slightly increase the laser frequency to go above the lowest ionization threshold, and this is the threshold which corresponds to producing molecular ions only in the rotational ground state. Say if we park the laser frequency here, then we start molecular ions, producing molecular ions, and for energetic reasons, we can only produce them in the rotational ground state. And then we sympathetically cool them. And in this case, we produce the molecular ions, and they are then all sympathetically cooled into the Coulomb crystal. That is essentially the image that I already showed you before. These molecular ions that have all been produced in the rotational ground state and then sympathetically cooled. So in this way, one gets in theory state pure molecular ions, which are also translationally cold. So they are all in the vibrational ground state, they are all in the rotational ground state. And as a matter of fact, this was actually the easy part of the experiment. The hard part of the experiment was to prove that this really works, right? In order to prove this, you have to do molecular spectroscopy on these ions to read out the populations in the different rotational states. And that actually turned out to be the hard part of this experiment. Because in here, as I've already said, we have around 24, 25 molecular ions. So one needs a very sensitive spectroscopic technique to detect spectroscopic excitation in such a small ensemble, right? I mean, this is really homeopathic, if you like. Right, we only have 20 to 30 ions here on which we want to do spectroscopy. So what can one do, right? And at this point, it actually helps if one also knows a bit about chemistry, because these chemists, they tend to have a couple of tricks up their sleeve. And one of them is one can use actually chemical reactions to detect the spectroscopic excitation. And that is called action spectroscopy, because one detects the spectroscopic excitation by a specific action. And in this case, in our specific case, what one can do is it has actually been known for quite some time that N2 plus ions, nitrogen ions, can undergo a charge exchange reaction with argon atoms. So an electron hops over from argon to N2 plus, and one gets neutral nitrogen and argon plus. But this only works if the nitrogen ions are vibrationally excited. And the reason is there is a small mismatch in the ionization energies between nitrogen and argon, and one needs some extra energy in the vibration of the nitrogen to make this process energetically possible. If the nitrogen ions are in the vibrational ground state, this doesn't work. Yeah, and now you can use this to detect a spectroscopic transition very sensitively. So we use this to map out the rotational state populations of our state selectively produced ions in the following way. So we took another laser beam, and then we excited these state selectively prepared molecular ions out of different rotational states to an electronically excited state. And from there, eventually it would fluoresce back to the electronic ground state of the molecule, populating vibrationally excited states in this fluorescence with a probability of 55%. 45% would go back to the vibrational ground state, but 55% would go to vibrationally excited states. And and those we can detect then with the charge transfer scheme, right? Because those will then undergo charge transfer with argon. The nitrogen ions will disappear from, they will be neutralized, they will disappear from the Coulomb crystal. And this is something we can see in the images. And that is shown here, right? So these are nitrogen ions in the crystal before this laser-induced charge transfer scheme, as it is called, and here afterwards, right? After this excitation and fluorescence back to vibrationally excited state. And again, using simulations, one can analyze this. Initially, we have 24 ions. Afterwards, we have 12 nitrogen ions left. So 50% have gone away, meaning 50% have ended up in vibrationally excited states when they were pumped out of here. And so this is 50% is very close to this 55%, which is theoretically possible. So if one does a bit of statistic now, then one realizes that about 93% of the ions were in the rotational ground state, and not in rotationally excited states. Okay, so this is a way to do spectroscopy on the ions, and at the same time prove that the state selective generation of the ions really works. Okay, so I should also say that, I mean, these were the very first experiments that have been done to state selectively produce ions. Time has gone on, and a range of other techniques have also been developed to address this problem. For instance, there have been some very beautiful experiments, again, from Michael Drefsen's group, where a combination of sympathetic cooling and helium buffer gas cooling, so cryogenic helium buffer gas, was then used to cool the internal degrees of freedom by collisions. Then there was also a variation of rotational laser cooling using broadband excitation with femtosecond lasers, implemented by Brian Odom's group. We have also buffer gas cooling of molecular ions by ultracold atoms. This has been demonstrated by Eric Hudson's group. And there are also ways for probabilistic state preparations of ions, right? So projecting ions into a specific quantum state by just measuring this quantum state. And this has originally been proposed by Michael Drefsen in this paper here, and this has been implemented in our own laboratory, or a fashion of it has been implemented in our own laboratory very recently. So this is all the techniques that are essentially available at this particular moment. So that is another good point to ask questions, if there are any.
Yes, there are a few questions, so I will take them one by one. So first of these is, how do you detect the rotational state population and verify if optical pumping schemes work?
That's a very good point. So I will actually talk about this in the next part of my lecture, how they did it. They also did a type of spectroscopy, but a different flavor of spectroscopy compared to what I have shown you for our experiments. But I will come back to that in a few minutes.
Right. So then let's move to the next one. One of the methods you mentioned for measuring the temperature of the iron crystal is to compare your experimental result image with the simulation image. Mm-hmm. This is somewhat like an indirect method. Can we use radio frequency excitation to get an idea of the secular frequency and hence the temperature? What are the other direct methods?
So, yes, you can also use excitation methods, right? Coupled with ion ejection methods in many cases to get an idea about the temperature. Right? I mean, I think Sadik, especially yourself, you have used these sort of techniques many times to get an idea about ion temperatures. There are other direct methods, which I partly will discuss over the course of my lecture. You can do, if you are in the resolved sideband regime, you can do things like Rabi thermometry. You can also do a recooling type of spectroscopy, right? If the ions are hot, right? And then you can just track the time for how long it takes until they cool again. And this gives you also some ideas about the initial temperature. So there are various ways, yeah. The simulations are very nice for big ion crystals. They don't work well for small ion crystals, and for small ion crystals, one would use other techniques like sideband thermometry, which I will also discuss very shortly, and which I think have also already been introduced by Didi Leifrid yesterday.
Right. So let's move to the next question then. In the detection scheme for rotational cooling, do you use the single atom readout of the 25 N2 plus ions?
In these particular experiments that I have shown, not, yeah. But in later experiments, which I will discuss also shortly, we do that. We do exactly that. Yeah, we do a single readout.
One more question. Why does the second image after laser-induced charge transfer look a bit squashed?
So this is an excellent question. So I presume it refers to, let me see, this one here. Yeah. So indeed it is asymmetric. Yeah. And the reason is that we have radiation pressure coming from the right-hand side here, which pushes the laser-cooled calcium ions, which fill up these holes to the left-hand side. Okay, and I see with squashed, you probably mean that the crystal looks a bit like eaten away. Yeah, very good. This is a very perceptive remark. So what is happening here is also that in our experiment, So this takes several minutes, right? And the pressure is about 10 to the minus 10 millibar, but we still have a bit of hydrogen left in the background vacuum. And this hydrogen reacts with the calcium ions to give calcium hydride. And these calcium hydride ions are then sympathetically cooled at the outskirts of the Coulomb crystal. And this is what causes this squashing here. So very good question. Thank you.
Yeah, I think that kind of sums up this round.
Okay, very good. Then let's move on with the next part of the lecture. So all these techniques that I have been talking about so far, yeah, they can now be used for useful things, right? And one useful thing is, for instance, spectroscopy. And there are many different techniques in ion spectroscopy around that have been developed for decades, right? So why do such a complicated experiment as we and others are doing now? And the answer to that is that the advantage of these cold and controlled ions is that there are prospects to do spectroscopic experiments very precisely. So it's about precision spectroscopy. And why is precision spectroscopy interesting? Well, there are different applications that you can think of, right? You can use a very precise spectroscopic measurement in a specific system to come up with new types of clocks, right? So instead of atomic clocks, you can think of atomic ion or molecular ion clocks. And this is also actively pursued these days. Very precise spectroscopic measurements can test the validity of our basic physical theories like quantum mechanics or quantum electrodynamics to an exquisite degree of precision. One can test, fundamental ideas that are around. For instance, is there maybe a time variation of fundamental physical constants? For instance, the electron to proton mass ratio. Yeah, molecular spectra very sensitively depend on this number here. And in case these constants vary with time, right, this should be reflected in molecular spectra, which one then could measure or should measure very precisely. There are also ideas, or not only ideas, but also real experiments which use precision molecular spectroscopy to search for new physics. For instance, to determine the size or the magnitude of the dipole moment of the electron, right? And this then ties into the question of post-standard model theories. There are also questions, are there fifth forces and manifest themselves in molecular spectra? Are there maybe extra dimensions which could also influence molecular spectra? So these are questions that are being asked. And also in a question of more relevance to molecular physics, maybe if you think of more complex molecules, then you have often molecules that appear in two different forms, image and mirror image. And then the question is there a slight energy difference between them, right? And it has been, and nature has chosen one specific form of these molecules, for instance, of all the amino acids and sugars, only a specific form is used and not the other. And the question is why is that? There seems to be some interference now. Yeah. So.
Hello, can everyone switch off their mics, please, except for Stefan?
Okay, now it seems to be good. Thank you. Okay, so these are all motivations why one would like to pursue extremely precise spectroscopic measurements on molecules. Yeah, so how to do this, right? One needs to do spectroscopic measurements on cold molecular ions. I've already introduced one method, laser-induced charge transfer, or more generally, laser-induced reactions that can be used to detect spectroscopic transitions. Another possibility is photodissociation spectroscopy. And that has been used by many other groups in a range of other systems, MGH+, which I've already talked about. So here the populations were read out with photodissociation spectroscopy, or notably also HD+, where this has been used with great success. And this is an experiment from Stefan Schiller's group, where they are particularly interested in precision measurements of HD+ ions. the fundamental molecular ions, one of the simplest there is, right? Hydrogen molecular ions. So what one can do in these cases is they are interested in infrared spectroscopy. And so they take a first laser to excite the vibrational overtone in this molecule with an infrared laser, and then take another laser in the UV to photo dissociate the molecular ion once it has been excited to this excited vibrational state with another photon, and then they detect this photo dissociation event. Okay, because then the molecule is destroyed, and this changes the composition of the Coulomb crystal. And specifically, in these experiments done here, what they did is the following. They used beryllium ions to sympathetically cool Hd plus ions. I should mention that in order to get efficient sympathetic cooling, the masses of the coolant, here beryllium, and the ion to be cooled, here Hd plus, should be roughly similar. They shouldn't differ too much. So this is why beryllium was chosen to sympathetically cool Hd plus. And so this is again a bicomponent Coulomb crystal. It also already contains a bit of D plus in here as an impurity. And in order to determine the composition of this crystal, what has been adopted is a type of resonant excitation mass spectrometry. So the different ion species in the trap, they have different motional frequencies, because the oscillation frequency of an ion in a trap depends on its mass. So in principle, they oscillate with different frequencies. And one can then apply an additional oscillating electric field to the trap electrodes and resonantly excite the ion motion for different species, which differ by their mass. And this excitation then couples heat into the crystal, and the heat, and this then changes the fluorescence of the crystal, as we have already seen before. And so in this way, this is a way to do mass spectrometry actually on such a crystal and figure out what sort of ion species are in this crystal. And of course, if in the course of this photodissociation spectroscopy, Hd plus ions are photodissociated, giving D plus ions, and this then shows such a resonant excitation experiment where continuously the ions were excited here and then photodissociated. And one can see the Hd plus signal, which is this peak here, which diminishes as a function of time. And instead, another signal comes up. This is this D plus signal here from the D plus ions that are generated in this photodissociation. So this is a blow up here of this curve here. So in this way, this photodissociation event can be detected, right? And again, the photodissociation happens if the molecular ions have been excited beforehand by this infrared laser. And that is again a detection scheme which you can then use for spectroscopy with this infrared laser. This is shown here. This then shows a specific rotational vibrational transition in Hd plus. It's broadened by hyperfine structure. There's hyperfine structure lying underneath that. And but in this way, it is impossible to map out these spectroscopic transitions. So these sort of schemes have been refined over the years. And this is a very recent experiment from the group of Jérôme Colomé in Amsterdam, also on Hd plus, where they have done Doppler-free 2-photon spectroscopy. Yeah, so I should say that the line with here is to a large extent caused by, well, the unresolved hyperfine structure, but then also by Doppler broadening, right, at the residual temperature of these ions in the trap. So what one can do in order to eliminate the Doppler broadening is using a 2-photon spectroscopy, yeah, 2 laser beams with a very similar wavelength that are introduced into the experiment in a counter-propagating fashion. Yeah, so in this way, the Doppler shifts cancel, and one eliminates the Doppler shift from the entire spectroscopic problem. So they had 2 laser beams. First one was exciting from V equals 0 to V equals 4, and then the second one from V equals 4 to V equals 9. Wavelengths have to be similar to get this Doppler cancellation condition. And then from V equals 9, they would then photodissociate and then detect the spectroscopic excitation again by this photodissociation scheme. Now, there is hyperfine structure underneath there, as I've already said. I don't want to go into all these gory spectroscopic details. Suffice to say that there is a forest of lines underneath. And with this Doppler-free scheme, they could then really resolve different hyperfine components, right? So mind you here, this is a kilohertz scale now. And before here, we had a megahertz scale, right? And all these lines which were unresolved can now, with such a Doppler-free scheme, be resolved. Yeah, so it's a very nice experiment. And what they then did with this technique is that they used this in order to determine the value of the proton to electron mass ratio very precisely. Yeah, so not the time variation, but the value, the actual value of this ratio, and they compare this then to previous determinations, and to my knowledge, this is so far the most precise determination of this ratio. Yeah. So this is a very nice application of this technique. So I mean, this then begs the question. I mean, in the end, it's a quest for reaching ever more precise spectroscopic precision. And this now starts to raise the question, okay, so what sort of spectroscopic lines in a molecule should one pick for these sort of experiments? Yeah, ultimately one needs to measure them very precisely. So these lines need to be very narrow. And so that poses some quite stringent restrictions on lines that one can use. Because the width of a spectroscopic line is in its last consequence determined by its natural line width, yeah, meaning the lifetime of the excited state of this transition. And if this transition is dipole allowed, so if it is allowed within the electric dipole approximation of the coupling of matter with radiation, then it's usually reasonably strong. And consequently, its line width is rather broad. And one of the reasons why HD plus was chosen is that I mean the dipole this vibrational transitions that I addressed here, they are still allowed within the electric dipole approximation, but they are very weak because this molecule only has a very weak dipole moment. Yeah, because I mean it's isotopically polar, if you like. Otherwise, it would be an apolar molecule if it were H2 plus. And in these homonuclear diatomic molecules like H2 plus, or in our case, it's N2 plus, vibrational and also rotational spectroscopic transitions are not electric dipole allowed because there is no dipole moment in the molecule. So in this case, what can one do? These transitions only become allowed in higher approximations, higher order approximations, right? And the next higher order approximation, at least when it comes to the electric part of the problem, is the electric quadrupole approximation. So these vibrational transitions, they become allowed by quadrupole coupling of the molecule with the radiation. And but these transitions are then extremely weak. To put this into perspective, such typical quadrupole vibrational transitions are about 10 orders of magnitude weaker than strong dipole allowed infrared transitions in polar molecules. So they are extremely weak, but for the same reason, they are also extremely narrow and therefore interesting for precision measurements. And as a matter of fact, nitrogen has been proposed as a good system to test time variations in MP over ME, right? And it can also be thought of as a good system to implement molecular clocks, right, on this quadrupole transition set. Okay, so a few years ago, we set out to do exactly such experiments to, in the first stage, find these quadrupole transitions in nitrogen ions. And these vibrational quadrupole transitions, they have been measured in neutral molecules, a few, H2, N2, these sort of molecules, CO2 now, not too many, but those few. But to our knowledge, before this work, not in any molecular ion. And the reason are the formidable problems with detecting these extremely weak spectroscopic transitions. even more so in dilute samples as one usually has with ions. So what we did is the following. In the first incarnation of these experiments, we again had sympathetically cooled nitrogen ions in a Coulomb crystal, as usual about 20 to 25. And then we would excite these quadrupole infrared transitions with an infrared laser. In our case, it was a quantum cascade laser, which a highest power that we could get at the time. And we would just irradiate these transitions for a long time in the trap, about 2 minutes. And here, the big advantage of ion traps comes into play, that you can keep the ions for a long time in the trap and therefore realize experiments with very long interaction times. And then we would detect molecules that had been excited again by this charge transfer trick with argon. And that is a schematic of the experiment. We have an ion trap. I should also say how we introduced the nitrogen ions. Didn't say this before. Or the nitrogen molecules. We have a molecular beam, which is interfaced with the ion trap. And then here in the center of the ion trap, the nitrogen ions are then produced by state-selective photoionization using dye laser beams. Then we have laser beams for the cooling of the calcium ions. And then we also have, in this particular case, an infrared laser for the infrared excitation of the nitrogen ions. So also nitrogen is already a molecule with many gory spectroscopic details, right? I really want to spare this at this point, but suffice to say, of course, we have rotational structure superimposed on this vibrational transition again. Then we have spin rotational structure, we have hyperfine structure. So for a spectroscopist, this is all very exciting, but this is not the topic of the talk today. So suffice to say, we did an excitation from the vibrational ground state to the vibrational excited state. We picked an excitation where we start from the rotational ground state and then populate the second excited rotational state, and we were addressing different fine and hyperfine components in this transition. And that is a spectrum that we got in the end. After a long search, these lines are so extremely narrow and weak. As a matter of fact, it took us more than a year to find these lines. And then it took us another couple of months to take this spectrum. And what this spectrum shows here is hyperfine components out of this vibrational rotational line, some of them. And to our knowledge, this was really the first quadrupole spectrum of a molecular ion that had been recorded. So at that time, which is now some 7 years ago, we were extremely proud of this results. It was a very hard experiment. But at the same time, this experiment also shows the problems, right, associated with these technologies, right? I mean, the signal-to-noise ratio is quite poor here, and that after several months of work. So if one wants to measure these transitions extremely precisely, right, then this is not a viable way to go, right? So we need to improve the sensitivity of the detection scheme here. And I mean, in principle, the detection scheme is very sensitive, right? I mean, because we destroy the molecules, right? We can, in principle, detect a single excitation event, right? Because we can, in principle, in these experiments, we can count single molecules, as you have seen. But at the same time, by destroying the molecules, right? I mean, we then have to restart the whole experiment all over again, right? We have to, expel the ions from the trap, reload them, go through all the state preparation scheme again, right? Do the spectroscopy again, do this laser-induced charge transfer again. This takes time. So one experimental cycle takes a couple of minutes. Yeah. And so the duty cycle of all these experiments, also the photodissociation experiments, is very, very small, because you always destroying a sample. So there are two ways out of this, essentially. So one of them is, okay, you could say, okay, I need more statistics, so let's use just more particles, right? Fine. That's not what we did. So we did the exact opposite. We took less particles. To be more precise, only one. But then we changed the detection scheme in a way so that it becomes completely non-destructive. And that now brings me to the last topic of my talk, which is molecular ion quantum technologies and their application to spectroscopy. But before we start here, I think it would be another good opportunity to take a few questions, if there are any.
Right. There are none in the chat box. So can I take the liberty of asking one, Stefan?
Sure.
Right. So when you do the charge exchange with the argon, how do you put the argon beam into your crystal and not affect everything that is there already? I mean, it does the charge transfer with the nitrogen. And I mean, what are the parameters that actually you have to keep in mind when you are doing this argon-based charge
Okay.
transfer?
Very good question. Thank you. So the argon is introduced into the experiment by a leak valve. Yeah, and we use only very small partial pressures of argon. Of course, there is the problem that it could affect the molecular ions in a different way as well. Yeah, for instance, by inelastic collisions. But it turns out that, interestingly, the inelastic collision rate between argon and N2 plus is very small. It's only a fraction of the elastic collision rate. So this means that the introduction of argon, right, does on the timescales of our experiment not really change the state of the molecule. And moreover, the whole detection is performed after, in this case, the infrared excitation. But once the charge transfer experiment is done, right, it's of course over, right? I mean, then we have to, reload re-initialize the entire experiment, load again, and what have you. Does this answer the question, Sadiq?
Yeah. That answers the question. So the partial pressure is like you still maintain 10 minus 10 overall in your.
So we go a few times 10 to the minus 9.
Okay.
In this case, yeah.
All right. Yeah, I think please carry on. There are no further questions in the chat.
Okay. Thank you. Okay, then let me come to my last topic of today. This is molecular quantum technologies for ions and their application to spectroscopy. And now I need to dwell a bit on some details of the quantum motion of the ions in the trap. And I have seen that the Didi Leibfried has already covered this as well yesterday. So I'm very grateful to Didi, because then I can cut this short. So, but just to briefly recapitulate that. So we have an ion in a harmonic trap. Let's restrict ourselves to a single ion in this harmonic trap for the time being. And if you think of it from a quantum mechanical perspective, then, as I've already said, these traps are all designed that they produce a harmonic potential. And so we can think of the whole problem as a quantum harmonic oscillator. Yeah. So the oscillation, the motion of the ion in the trap can be understood as a quantum harmonic oscillator. And then, you can apply all the machinery that you have learned in your freshman quantum mechanics class, right, about harmonic oscillators, right? So we have quantized energy levels of this harmonic oscillator. We have 0-point energy, right? We have equidistant energy levels between the motional states are equidistant on an energy scale, and all these sort of things. So, and moreover, what you can then do is you can start to address these harmonic oscillator levels in your experiment. And you have to think about it in the following way. So now let's assume we have a single ion in the trap. For the sake of simplicity, it's an atomic ion, and we pick two energy levels from this atomic ion, say two different electronic energy levels, a ground state and some excited state. And then on top of that, we have these harmonic oscillator energy levels of the motion of this ion in the potential of the trap. So if we put those two together, right, then if you will, we get something like a quasi-molecule, right? So we have the electronic degrees of freedom of this atomic ion, G and E, and superposed on that, we have the motional degrees of freedom, right? A bit similar to the vibrational degrees of freedom in a molecule. Right? But here it's the motional degrees of freedom of the ion in the trap, and which are then superimposed on the internally electronic energy levels of this ion. So After Doppler laser cooling, such an ion is typically, it's cold, right? Typically around the millikelvin if you run your experiment well, or even a bit below that. And but it's not yet in its motional ground state, right? Quantum mechanically speaking. So the 0-point energy in typical ion experiments corresponds to a few microkelvin, right? And you usually do not get there just with Doppler laser cooling. So you have some additional, to do an additional step to really cool then the ion down to the quantum mechanical motional ground state of the trap. And one of the ways to do this is, for instance, resolved sideband cooling. And so to quickly recapitulate how this works. Yeah, so now let's assume that after Doppler laser cooling, our ion is in the ground state, in the electronic ground state, but it still occupies some excited motional state, say the state with two quanta in the motion. What one can then do is one can then excite the ion to its excited electronic state, but then drive the transition such, right, that one at the same time one de-excites the motion by one quantum. And this is called a red sideband transition because one quantum of motion is therefore eliminated from the system. And then the ion is populated in this excited state, right, with one quantum in the motion. It fluoresces back to the ground state. And as you probably have heard from Didi Leibfried yesterday already, then this fluorescence is most effective in a transition where the motional state is conserved. This is called the carrier transition. And so if it, then we go down back to the electronic ground state again, but then we are in the n=1 state, right? So compared to here, we have already lost one quantum of motion. Then you can do the trick again, another red sideband transition. Here go to n=0 in the excited state, fluoresce back, and at that point you are then in the motional ground state, and then you have really cooled the ion down to its absolute ground state. So this scheme is called resolved sideband cooling, and and this is one of the major schemes which is used to make the ions really ultra cold, at least along one specific mode. Of course, certain conditions have to be met here, and this was discussed yesterday by Didi Leibfried. You have to be in the Lamb-Dicke regime, right? So this means that the amplitude of the motion of the ions to start with must be smaller than the wavelength of the cooling laser that you use here, right? So this is why you need the Doppler pre-cooling. And of course, the bandwidth of your laser must be small enough to resolve these different sidebands. Yeah. And in typical ion trapping experiments in this fashion, right? So the motional frequencies of the ions are on the order of a megahertz, right? So the spacing between these levels is on the order of a megahertz. So you need a narrow band laser in order to resolve these different sidebands. So let me show you a concrete example from our lab. So of such an experiment. So this is an experiment where we have cooled down a calcium nitrogen 2-ion string to its motional ground state. And then that already ties into the later experiment where we then do spectroscopy on the nitrogen ion with these methods. And that is a preparatory step for that. So we have a calcium ion and we have a nitrogen ion. Again, you can't see the nitrogen ion because it doesn't fluoresce, right? But you know it's there. And we can then start to measure a sideband spectrum, right, of this calcium nitrogen 2-ion string, right? And we do this by exciting the calcium ion on a dipole forbidden electronic transition in this case. So this is the level scheme of calcium ion, in a bit more detail compared to what I've shown you before. And for this experiment, then one uses a transition from the ground state, the 4s1/2 state, to the excited D state. In particular, specifically the 3D doublet D5 state, which is around 729 nanometers. So this is a dipole forbidden transition, right? But it's allowed in the quadrupole approximation, right? Because the L quantum number changes by 2 units. So it's quadrupole allowed. So and this is at 729 nanometers. It's a narrow transition, and we use a narrow laser in order to drive this transition. And if you start taking a spectrum of this transition, right, in the resolved sideband regime, then this is what you get, right? You're not only getting one transition, right, per Siemens component even, right? But you get many different transitions, and what you see here are, what you start seeing here are the different sidebands. And the sidebands correspond then to transitions where you change the motional quantum number by 1 unit. Either you lose 1 unit, these are these red sideband transitions that I've already mentioned, or you increase it by 1 unit, that's a blue sideband transition. And in the middle, you have the carrier transitions. These are these transitions where the motional quantum number is not changed during this electronic excitation here. So if you now do resolved sideband cooling and cool the system down to the ground state of this harmonic oscillator, then this red sideband vanishes. And that is shown here. This is this red spectrum here. Yeah, it's essentially 0, because if you're already in the ground state, you cannot drive another transition where you yet lose another quantum. Yeah, because there's no state below the ground state. Okay, so when you are in the ground state, then this red sideband vanishes. Yeah, and then you really know you're as cold as you can get. And that is, by the way, another method which you can use for thermometry, right? By just measuring the strength of this red sideband transition. Okay, good. So this is now a prerequisite to do both quantum logic and spectroscopic measurements. And in order to explain how this works, I'd like to discuss a very famous experiment with you, which essentially triggered this whole field. And that was an experiment by the NIST group, now done more than 15 years ago, which dealt with the quantum logic spectroscopy of the 27 aluminium plus ion. So aluminium plus is one of the prime ions for setting up optical clocks. The problem with aluminium pluses is that it can't really be laser cooled easily because it has a cycling transition, but the wavelength of these cycling transitions is 167 nanometers, and that is not a nice wavelength to work with. So this means you can't really directly laser cool it. And in these ion experiments, trapped ion experiments, you also always use these cycling transitions for state readout. And so this can't be done here either. Yeah, so it can't be cooled, it can't be properly read out. So what do you do? And in this work, they came up with a scheme which they call quantum logic spectroscopy. And the basic idea behind it is that you do the spectroscopy on this aluminum ion, and the spectroscopy transition that they were interested in, this is the clock transition in aluminum. It's the 1s0 to 3p1 transition. This is the transition that they wanted to do spectroscopy on. So you do spectroscopy in this transition, but you read out spectroscopic excitation on a neighboring beryllium ion. And this beryllium ion is not only used for readout, but also for sympathetic cooling of the aluminium ion. So the detection scheme is by transferring the information on the spectroscopic excitation here to a neighboring beryllium ion and reading it out from there by fluorescence again, because there is beryllium can be laser cooled. It has an easily accessible cycling transition, which can be used for readout. So how does this work? So it starts with cooling both of these ions down to the motional ground state of the trap, yeah, or at least the motional ground state corresponding to one mode of motion in the trap, similar to what I have shown you before in our calcium-nitrogen experiment. And then going through such a quantum logic protocol. And yeah, this uses the following elements. They define 2 qubits. One of them is in the beryllium. It's called the logic ions. And here, the 2 qubit states are hyperfine components of the ground state, which are connected by a Raman transition. And in aluminium, they chose as qubit essentially the 2 levels associated with the spectroscopy transition that they were interested in. So how does this spectroscopic detection scheme now works? So it's a bit intricate, so I'll go through it slowly. So we start by putting both systems, the spectroscopy ion and the logic ion, into the lower qubit states. in the motional ground state. So both ions were initialized in these states. Okay, then the spectroscopic transition in aluminium was excited, taking it to the upper state of the spectroscopic transition, so the upper qubit state. After the excitation, it was de-excited again by a red sideband transition on the spectroscopy transition. Red sideband transition means, in this case, if you start with it from the excited state, then essentially it's the reverse. When you start from the ground state, it now adds one quantum of motion to the whole crystal. So, and because these two ions are coupled in the trap by the Coulomb interaction, it's essentially a combined motion of the two ions. So this also means that the logic ion, the beryllium ion, is then excited, is then motionally excited by this red sideband transition. And then they, in the last step, they then shelved the beryllium ion in its upper qubit state, so this excited hyperfine state, by a Raman transition, by a red sideband transition on the beryllium ion. But this only works, right, if the motion has been excited by this red sideband transition on aluminium to start with, right? That is the condition. So essentially this means is that at the point where this beryllium ion has been shelved in this upper qubit state, then the fluorescence breaks down, right? If they start interrogating it by fluorescence, right, then they don't observe anything because the beryllium ion has been shelved in a different state. And this only works if the motion has been excited beforehand. And this is only the case if the aluminium ion has been excited on a spectroscopy position beforehand. Okay? So in this way, information about the spectroscopic excitation of aluminium is transferred to beryllium and then read out from beryllium in this rather elegant manner. Yeah. And this is what was the first experiment on what is now called quantum logic spectroscopy. So they then used this scheme to ask some rather fundamental questions, right? For instance, they measured this transition in aluminium for for more than a year, and used this to constrain a time variation of the fine structure constant alpha over that year. And what they found is that, okay, within their measurement sensitivities, then they didn't find any statistically significant time variation of alpha in this case. But this again, this shows an application of these highly precise spectroscopic measurements within the realm of changing fundamental constants. Okay, so that happened already some 15 years ago. And then it took more than 10 years to apply these sort of ideas and techniques to molecular ions, right? And again, the problem is the increased complexity of molecular systems. And the first experiment in the realm of quantum logic spectroscopy of molecular ions came from Pete Schmidt's group, who was also involved in the first quantum logic experiments on aluminium some 5 years ago. And let me now quickly walk you through this to see how this works. So in this experiment, they also used magnesium hydride plus as the molecule that they wanted to study. And they were and they wanted to do a quantum logic spectroscopy readout of in this case, an electronic transition in magnesium hydride. So the experiment was like they had magnesium plus as the logic ion, which also served for the sympathetic cooling and resolved sideband cooling, and then they had magnesium hydride plus, which they wanted to probe spectroscopically with these quantum logic techniques. So the scheme here is a bit more involved. What they did is they implemented a motional qubit in the following way. So what I haven't told you before is that these ions, they have different modes of motion in the traps. It's not a one-dimensional harmonic oscillator, it's a multi-dimensional harmonic oscillator. If you have two ions in the trap, you have in total 6 degrees of freedom, so 6 different modes. And if you just think about the oscillation along the symmetry axis of the trap, you have 2 modes. One of them is the in-phase mode, right, where both ions oscillate in phase. And then there's the outer phase mode where both ions oscillate out of phase. And they then implemented a motional qubit in these modes, defined in the following way. The down state is the one where we have one quantum in the in-phase mode and zero quanta in the outer phase mode. And then the up state is where we have zero quanta in the in-phase mode and one quantum in the outer phase mode. And then they overlaid this ion crystal with an optical lattice. So focused counter-propagating laser beams. And this lattice was modulated at the frequency which corresponded to the frequency, to the difference of the motional frequencies of this outer phase mode and of the in-phase mode. So what this optical lattice did is its wavelength was chosen such that it was closely detuned from an electronic transition in the magnesium hydride ion. And in that way, so it was not on resonance with this electronic transition, but it was closely detuned from it. So in that way, it was prevented that this optical lattice, this laser beam, excites the molecule, but it was close enough detuned so that it would still produce a strong enough optical dipole force on it. Yeah, so an optical dipole force is generated by this dispersive interaction of this laser beam, in this case with the molecule. And the strength of this interaction, yeah, I mean, you can call it an AC dark shift or a light shift, this all boils down to the same phenomenon. This dipole force that is generated by this optical lattice is the stronger, the closer the system is detuned from a spectroscopic resonance in the molecule. So this is where the spectroscopic information comes into play. So what they then did is that whenever this optical dipole force was acting, meaning if the molecule was in the right quantum state in order to drive, in order to be closely detuned from this electronic transition, this optical lattice which was modulated at this difference frequency would then induce a rotation of this qubit. Can visualize this with a Bloch sphere picture. So this optical dipole force would then rotate the qubit from on the Bloch sphere as a consequence of this optical dipole force. Because this modulation would then actually lead to if you will, a sort of excitation of these motional modes, and therefore a rotation on of this qubit. And moreover, so the problem here in this experiment was that the optical dipole force was acting on both particles, on magnesium plus and on magnesium hydride plus. But the rotation was more pronounced than when the magnesium hydride plus was also in near resonance with this optical lattice. So this would then entail a stronger or a more pronounced rotation of this qubit. And this could then be read out again on the magnesium ion. And moreover, one could then read out or determine the rotation of this qubit as a function of the detuning of this lattice laser from the spectroscopic transition in magnesium hydride. And in this way, from the strength of this rotation, in the end, then map out the spectroscopic line shape that is associated with the transition from which the optical lattice was closely detuned. So that is, in a way, an adaptation of these quantum logic techniques to the world of molecular ions. It's a bit more involved than in the atomic case. Here they were really working with coming up with a molecular qubit that was constituted from different motional modes and inducing qubit rotation by an optical dipole force that was generated near a spectroscopic transition in the molecule. And then working back from this qubit rotation to the strength of this optical dipole force, and then measuring this qubit, and then measuring the tuning of the lattice laser from the resonance, and thereby gain spectroscopic information. on this on the molecular ion. So a similar experiment has also been implemented in our group recently on nitrogen plus in yeah, maybe a bit a more simpler fashion that does not need the implementation of such optical qubits. In our case, motional qubits. In our case, we were using a coherent motional excitation of the two ion string induced by such an optical dipole force. And just to also quickly walk you through this experiment, we have two ions in the trap, a calcium and the nitrogen ions. We ground state cool them again, here only in one mode, the in-phase mode of the calcium-nitrogen string. And then we also introduce an optical lattice, and this optical lattice laser wavelength is closely detuned now to a strong electronic transition in the nitrogen molecule. We would then modulate the lattice laser frequency by the motional frequency of these two ions in the trap, right? And this then, and if the optical dipole force acts on the nitrogen ion, and this is of course only the case if the nitrogen ion is in a very specific quantum state, yeah, from which it is near resonant then on this spectroscopic transition, then this modulated optical dipole force would induce a motional excitation of the ion string again. Yeah? And it's not a simple heating, it's actually a coherent excitation because it's a coherent drive that is exerted by this modulated optical lattice. So we would then therefore excite the motion of the ions again. And then one can read out this motional excitation by doing Rabi thermometry, right? So driving red sideband transitions again on the calcium ion in this case. And if no motional excitation has happened, meaning if no dipole force has acted on the molecule, then we are still in the motional ground state. And so we do not observe any Rabi oscillations on this red sideband transition. However, if motion excitation has happened, then we then observe Rabi oscillations on the sideband transition. And so this means that, and from the amplitude and from the frequency of these Rabi oscillations, we can then work back on the strength of this optical dipole force, and therefore from the detuning of the lattice laser from the spectroscopic transition. Yeah, this gives some more details about the energy level structure of nitrogen that is relevant here. I already said we have we use a strong electronic transition in nitrogen. Actually, it's exactly the same transition that we previously used in this laser-induced charge transfer experiment. Only here we use it for generating an optical dipole force. Again, we have different rotational components, and we were focusing on a case where we prepared the ions in n equals 0 and j equals 0, so in the absolute ground state of the molecule, particularly rotational ground state. And then these blue curves here shows the strength of the optical dipole force as a function of the detuning of this lattice laser. We would then put the laser frequency very close to the center of this profile here, where in the center we have the resonance condition. So we are very close to the resonance to create a strong optical dipole force in order to perform this experiment in the end. So this can also be used to read out and detect the quantum state of the molecule, right? Because this only works if the molecule is really in the rotational ground state. And if one does a bit of statistics, then one realizes that one can do a state readout measurement here with a fidelity of more than 99%. Yeah. And so this can be done very sensitively. And the reason is, and you can do this because it's completely non-destructive. Yeah. So one does not destroy the molecule in this readout scheme anymore. One not even changes its quantum state, right? Because it's a completely dispersive interaction in the end, right? So we do not excite the molecule really, right? We only, create an optical dipole force close to a resonance. Yeah. So it's chemically non-destructive and quantum non-demolition. So we can recycle the same molecule over and over again, and in this way boost the duty cycle of the experiment by, in our case, 4 to 5 orders of magnitude. Yeah, and that is way more sensitive than any destructive detection scheme that has been used before. Okay, good. So I had to speed up a bit in the end in order to not take up too much of your time. So I'm essentially finished with this part now. I should also say that there are now this is now a new and growing field. This molecular ion quantum technologies. There are already a range of other exciting experiments as well. For instance, from the NIST group, where they also did various types of spectroscopic experiments and also quantum entanglement experiments with atomic ions. And so this is a field that is really just starting at the moment. And I believe that many more exciting developments in this realm can be expected in the very near future. Okay, so this brings me to the end of my lecture today. And I'm happy to take any further questions if there are any.
So sideband cooling is radial, I guess. So is it possible to do it from the axial direction also?
In our case, it's actually axial. But yeah, I mean, you can do this from any direction. Yeah, in principle.
A related question is, what is the time scale of quantum logic protocol technique?
So one complete cycle takes 20 to 30 milliseconds in our case.
Right.
Yeah. So one single readout experiment takes 20 to 30 milliseconds.
Yeah. So right. That's when you were not doing the quantum logic.
That's right. Yeah.
Yeah. Okay. So for two ions in the same trapping well, how does the Coulomb repulsion affect the motional states, perturbatively or non-perturbatively?
Yeah, that's something I didn't really go into the detail, and so I thank you for this question in order to clarify this. So essentially, you can't. It's a strong interaction, so you can't really treat it perturbatively anymore, right? So you really have to treat it as a strongly coupled system, and you have to think in terms really start thinking in terms of normal modes. Of the ions which are coupled by the Coulomb interaction in the trap. So it's and normal modes, meaning that the motion of the ions is really highly synchronized, right? And this is what I showed with the example of the in-phase and of the out-of-phase mode, right? So you have an in-phase mode then of these two ion string where both ions then essentially oscillate in phase together, right? And the outer phase mode is then they oscillate against one another. So you really have to treat these as a strongly coupled system. And again, one can make an analogy with molecules here, right? In which the atoms are also strongly coupled together in a molecule, right? And you also have to think here of the vibrational modes in a molecule. You have to think of them in terms of normal modes.
Right. I think I don't see any further questions. So so I think we can thank Stefan for a lovely presentation and look forward to his next one.